In the last few videos we've seen a lot about determinants, but our approach has been very algebraic. We wrote down a formula for the determinant and we proved various properties of how it behaves under row operations and things. But we haven't really seen any geometry for a while, and I want to rectify that. So theorem, let A be a 2 by 2 matrix, let S be the unit square in R2. In other words, it's, if you take the x and y axes here, it's the square that sits here and has side lengths 1 and 1. And finally let AS be the image of S under the geometric transformation corresponding to A. Then the absolute value of the determinant of A has a geometric interpretation. It's the area of AS. So what is AS? AS is going to be a parallelogram. Let's see an example. Let's take A is 1, 1, 0, 1, which represents a shear in the x direction. So if I apply this shear to my square, it gets kind of tilted in the x direction, and you end up with something that looks like this. So this is 1, 0. This point here is what I get by applying A to 0, 1. So that's 1, 1. And this vertex here is what I get by applying A to 1, 1, which is 2, 1. Let's check the formula. The area of this parallelogram you can compute by subdividing, say cutting it into 2 triangles and then moving this triangle over here just by parallel motion, so that you get this square back. So this is the square you started with actually. So this square has area 1, so the parallelogram also has area 1. So AS has area 1, so det A equals 1. And that's true, right? 1 times 1 minus 1 times 0 is 1. So let's prove this theorem, and the proof is going to be a proof by dissection, just as we computed the area in this example. So here's my parallelogram. There's one edge, there's another edge. Just to make sure they're parallel, I'm going to do it like this. Okay, what are these edges? This edge here is A applied to 1, 0, which is just the first column of A, which is AC. This edge over here is A, 0, 1, which is BD, the second column of A. So what I'm going to do is I'm going to draw a rectangle. If I call this a square, I've re-recorded this like about 3 times already. If I call it a square, it's a rectangle. Okay, it's got height D, which means it's going to pass through this vertex here, and it's going to have base A, which means it's going to pass through this vertex here. There we go. Okay, so this is a rectangle. A by D. Its area is AD. So what I'm going to do is I'm going to subdivide the parallelogram into pieces, shift them so they live inside this square, and then see that there's still a bit missing, which is going to have area BC. That's the strategy of proof. So I'm going to draw a little blue arc connecting the top right of the rectangle to the top right of the parallelogram. And now I've now cut it into three pieces. There's this green piece up here, there's an orange piece here, and then there's the part that lies inside the rectangle. So I'm now going to move the green region downwards and in so that it fits into this hole underneath the parallelogram. And I can do that because this edge of the parallelogram is parallel to the bottom edge of the parallelogram. So when I do this, this blue line will end up down here, and the green region will end up down here. I do the same for the orange region, moving it over here. So I've now gotten rid of everything outside the rectangle. But I haven't changed the area of the parallelogram, right? So if you take this blue region, this orange region, and this green region, the total area is the same as the area of the parallelogram we started with, because I've just cut it up and rejigged the pieces. So what's missing? There are these two grey triangles. So in other words, the area of the rectangle AD minus the grey area is the area of the parallelogram. Which is AS. So we just need to check that the grey area is BC. That'll tell us that it's the determinant. Why does this work? Well, looking at these two triangles, they both have a blue edge, and remember the blue edges are all parallel. They were obtained by taking a blue edge up in the top right and translating it around. So they're parallel. That means these two triangles just glue together to make a rectangle. With a blue line going across it. And what is the area of this? Well, this vertical height is the y coordinate of this vector AC, so that's C, and the width is the x coordinate of this vector, which is BD, so that's B. So the area of this rectangle is BC. So that proves the formula for the determinant and the area being equal.